A star millions of times heavier than our sun stops fighting. For millions of years it burned with impossible fury, light against gravity, pressure against collapse. Then the fire dies, gravity wins. The star falls inward faster than anything you can imagine. Its surface disappears. Its core collapses. Space itself begins to fold. Light cannot escape. Time refuses to behave. And somewhere beyond that invisible boundary, reality breaks. Now imagine you're floating there, no engines. No rescue. No signal, only silence. The darkest silence in the known universe. Ahead of you is a perfect sphere of absolute blackness, not darkness. Absence. The place where the universe hides its greatest secret, a black hole. You've probably heard that nothing escapes it, not light, not matter, not information. But that raises an even more terrifying question: what actually happens inside? Let me explain why this question has haunted physicists for generations, because once you cross that boundary, the universe stops giving clear answers, and everything you thought you understood about reality begins to collapse. You think the universe is chaotic. Exploding stars, colliding galaxies, violent supernovas. Gamma ray bursts brighter than entire galaxies, but here's the cosmic truth. The universe isn't chaotic, it's astonishingly organized. Every collapsing cloud, every orbit, every explosion, every birth of a star, they all obey invisible rules. That's not chaos. That's gravity. Gravity is the architect of the cosmos. It builds stars, shapes galaxies, creates planets, and eventually destroys everything it creates. A black hole isn't an accident. It is gravity reaching its ultimate conclusion. When enough mass is squeezed into an impossibly tiny region, space bends, then folds, then traps itself. Imagine stretching a sheet, place a bowling ball in the center, the sheet bends. Now imagine replacing that bowling ball with something so massive, the sheet tears. Not because space is fragile, but because gravity becomes stronger than every force trying to resist it. This isn't random. It's the law of the cosmos. Black holes aren't monsters hiding in the universe, they're consequences. The inevitable result of nature following its own equations, and once something crosses the event horizon, there is no known path back. Not because something blocks the exit, because every possible future points inward. The event horizon isn't a wall. It isn't a surface. You wouldn't feel yourself passing through it. There would be no alarm, no explosion, no flashing lights. If the black hole is large enough, you might not notice anything at all. That's what makes it terrifying. You keep drifting, everything feels normal, your heartbeat, your breathing, your thoughts. Yet somewhere behind you, the entire universe has become unreachable. The event horizon is a one-way boundary. Cross it, and every road leads deeper. Imagine standing at the edge of a waterfall, far upstream. The river moves gently, closer. The current strengthens. Eventually, the water moves faster than you can swim, no matter how hard you try. You cannot go back. The event horizon is that point, except instead of water, it is spacetime itself flowing inward. You are no longer moving through space, space is carrying you. Now the real journey begins. As you fall, gravity becomes uneven. Your feet are slightly closer to the black hole than your head. That tiny difference grows rapidly. Your feet fall faster, your head falls slower, the stretching begins. Physicists call it tidal forces. The nickname is far more disturbing: spaghettification. Your body stretches. Your atoms separate, your molecules resist, chemical bonds break eventually. Even nuclei cannot survive. You become a stream of particles pulled into impossible geometry for a small black hole. This happens before you cross the horizon for a supermassive black hole. You might cross the horizon intact only later. Far inside, would gravity become overwhelming, the destination remains the same. The timeline changes. Now imagine someone watching from far away. They see something extraordinary. You never appear to enter the black hole. Instead, you slow. Your movements become sluggish. Your light grows redder, dimmer, fainter. Eventually, you freeze. From their perspective, you remain suspended forever near the event horizon, but from your perspective, nothing unusual happens. Your watch keeps ticking, your thoughts continue. You fall. Two realities, both correct. This is one of the strangest predictions of Einstein's general theory of relativity. Time is not universal. It depends on where you are, near enormous gravity. Time stretches near a black hole. It nearly stops relative to distant observers. This isn't science fiction. It is one of the most precisely tested ideas in modern physics. The same effect, though far weaker, is measured by satellites orbiting Earth. Their clocks tick at slightly different rates because gravity changes the flow of time. Every path inside seems to end at one destination, the singularity. A place where our equations predict infinite density, infinite curvature, infinite gravity. But infinities in physics usually signal something else, not that reality has become infinite, but that our theories have reached their limit. General relativity describes gravity with extraordinary accuracy. Quantum mechanics describes the microscopic world with equal success, yet inside a black hole, these two pillars refuse to agree. One predicts relentless collapse. The other insists the quantum world cannot be ignored. Somewhere in that conflict, the true nature of the singularity is hidden. Perhaps it is not a point at all. Perhaps it is a quantum state we have not yet learned to describe. The truth is, we do not know, and admitting that uncertainty is part of science. Here is another mystery. Imagine throwing a book into a black hole. Every word, every photograph, every memory encoded in its atoms, gone. Or is it? Quantum theory says information cannot simply disappear. General relativity seems to allow exactly that. These two ideas collide in what physicists call the information paradox. For decades, researchers have proposed possible resolutions. Some suggest information is subtly encoded on the event horizon. Others argue it escapes through delicate quantum effects associated with Hawking radiation. Some even propose entirely new ways of thinking about spacetime itself. No single explanation has been confirmed, but the search has reshaped modern theoretical physics. In 1974, Stephen Hawking proposed something astonishing. Black holes are not completely black. Quantum effects near the event horizon allow them to emit an extremely faint glow over unimaginable spans of time. They lose mass. They slowly evaporate. For stellar and supermassive black holes, this process is incredibly slow, far longer than the current age of the universe. But the implication is profound. Even the darkest objects are not eternal. The universe changes everything. Given enough time, even giants fade. Let's leave theory for a moment. In 2019, astronomers revealed the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87. The glowing ring surrounding it came from hot gas racing at enormous speeds. The dark center marked the region where light could no longer escape. Years later, astronomers also produced an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way. These images did not show the singularity itself, they showed gravity sculpting light. Elsewhere in the universe, telescopes have watched stars wander too close to supermassive black holes. The immense tidal forces tear those stars apart in spectacular tidal disruption events. Brilliant flares erupt as stellar material spirals inward, heating to millions of degrees before disappearing beyond the event horizon. The universe does not merely create black holes. It reveals them through the fate of everything that ventures too close. Now imagine yourself again, floating toward that silent sphere, no sound. No wind, no up, no down. Just gravity. Would you fight? Would you panic? Or would you accept that every atom in your body was forged inside ancient stars, only to return to one of the universe's most mysterious creations? Perhaps black holes are not simply cosmic prisons, perhaps they are reminders that nature does not exist for comfort, it exists according to laws. Elegant, unforgiving, beautiful. This isn't random. It's the law of the cosmos, every star that shines, every galaxy that spins, every black hole that waits in silence is part of the same grand design. And maybe the most unsettling truth isn't that black holes swallow light, it's that they expose the limits of our understanding. The closer we look, the more mysterious reality becomes. So, what happens inside a black hole? The honest answer is both fascinating and humbling. We know what happens outside with remarkable confidence. We understand the event horizon, tidal forces, gravitational time dilation, and the evidence that black holes truly exist. But beyond that horizon, the universe keeps its greatest secret for now. Every new telescope, every gravitational wave detector, every advance in quantum theory brings us one step closer. Until then, black holes remain more than astronomical objects. They are questions written into spacetime itself. Questions that challenge everything we think we know, and perhaps one day, the answer waiting inside a black hole will completely rewrite the story of the universe if that day comes. It won't just change physics. It will change how humanity understands reality itself, because the deepest mysteries are rarely hidden in darkness. They're hidden at the edge of what we can explain.